function okay, so it is the index of point Z in the open set. So it is an open set. So that is the open set. So you can see that this function is well defined the open set. So every point Z in the open set has a definite value, okay, and this value is called the index of the point Z. Now, so we first show that the index function, okay. So basically, the index function is function from the open set to the complex plane, so it's a complex value function. Okay, it's a complex value function. So we first show that it's continuous, right? So we'll show it's continuous omega. Okay. So now the proof is like here. So we first fix a point Z in the open set. We'll call Z 0. Right now, since gamma of E minus Z0 is a continuous function, okay, so this is a continuous function on the parameter interval. Okay, how about the beta? Right? Why? Because gamma is a continuous function, of course. Right? So it's and we know actually it's piecewise differentiable. So, but anyway, so it is continuous, and by definition, and so you minus a constant here. So of course this is a continuous function. And when you check the absolute value, of course that value is also a continuous function. Okay, so the whole thing that is a continuous function on the parameter interval. Okay, okay, and look at this one. So and this is a complex interval. It's complex set, right? I mentioned in Rn, especially in R1, any bounded and closed subset is compact. So, which is compact. Okay, and so this is a continuous function on such a compact subset by the extreme value theorem. The extreme value theorem, it has a so by the extreme value theorem, okay, gamma Z0, okay, is greater than or equal to minimum, okay, for some n greater than or equal to 0. Now, since Z0 is not in the image of gamma, because Z0 is point in the open set, and the open set is a complement of gamma star. So we know Z0 is not equal to. So M and B use D to consistent with my measurement. So the D must be greater than 0. Because what? Well, I think I have some. I think I have to define this as B. Okay, the minimum. Because by extreme value theorem, the minimum is achievable. Okay, achievable. So we define this as D. And so because Z0 is not, so this difference cannot be 0 anyway. So the minimum should be greater than 0. All right. Okay, now since omega is open, there exists a neighborhood of Z0, right, contained in omega. Okay, so omega, because that, for example, this is gamma star. All right, so we have, for example, we have Z0 here. Okay, and because omega, the complement of gamma star is open, so we have this neighborhood, okay, contained in omega mixture. This neighborhood does not intersect with the image, the curve. Okay, that's the real meaning. So when we say that this neighborhood is contained in omega mixture, the whole disk does not intersect with gamma star. Okay, so now the things we use so gamma t minus Z0. Remember, the side will run through points. Okay, so actually, when you do the line integral, you know that here we have sine, which is gamma t, right? So for every t, okay, for every t in the parameter interval, there is a point psi, and moving through depends on the orientation. Okay, I didn't specially say okay the orientation is counterclockwise. So along this line integral, all right, the psi actually is equal to gamma t, and so the denominator is gamma t minus z, right? Now we fix a z0 first, right? So now the denominator actually is less than or equal to gamma t minus z plus z minus 0. Okay, and okay, so we have so we can select, the situation is that we select something like we select a row, okay, and the row is less than or equal to half of d. Okay, we can always select a neighborhood. This disk has radius which is less than or equal to d divided by 2, right? This d. Okay, so if d is small, that's fine. We can find a row very small, than less than or equal to d divided by 2. Okay, so this is our situation. So now okay, and so that gamma t minus z, okay, only minus z is greater than equal to gamma t minus z0 minus z minus z0. Okay, so you just move this term to the different side, so you get that. And so this is greater than, because the minimum is d, okay, and the distance. So we want for all z in the neighborhood. So actually, I just say this is a disk with z0 as center and the 0 here. Okay. So for all z here, okay, for all z here, okay, we have this is so this is because because here this one is less than equal to rho. Oh no, it's less than rho for all in the disk. Right? This is by definition of a disk. So the difference is less than rho, and so so we have a low bound, okay, because rho is bigger than this one, right? And so this is greater than equal to d minus d divided by 2, because rho is less than equal to d divided by 2, and so this is d divided by 2, and this is fine. So you see that we have this estimate. Okay, so that so now for all z in the disk, right? For all z in the disk, the index value, right? Now we estimate the difference. Okay, so the index of z in the disk in this neighborhood, minus the index of the center is 0. All right, and so this is by definition. Okay, we take the f value, so this is 1 minus. Okay, right here. Okay, and so so the calculation we have okay, and z minus z0. Okay. So this is the difference. And so when we take the x value, we know this is equal to, okay, and alpha to beta. So so when we do that, so we have z is 0, gamma t minus z, gamma t minus z0, gamma t and dt here. Okay, by definition of the line integral. All right, and now this is constant, right? It's independent of t, so we can and basically we know that, right? We know here. Okay, so when we move the absolute value sign into the integrand, we have inequality. And okay, and so so this is z minus z0 2 pi alpha beta 1 over gamma t and z x value, gamma t minus z0 x value, and gamma derivative. Alright, so now we know this one has low bound. Okay, gamma t minus 0 would be epsilon divided by, you cancel, so it's pi d square and the gamma here, such that the function value index of z minus index of z0 is less than delta, say epsilon, for all z minus z0 is less than epsilon. Okay? So, well, the epsilon actually is rho. Maybe I just use rho. Okay? Because I use rho as the neighborhood. So, I think my specification is that I want this epsilon. Yeah, okay. Sorry. I want this to be epsilon. So I need delta. I need a rho. Okay, is equal to epsilon pi d square gamma. Okay. Yeah. So there exists this one, and equal to this. So you see that you said for all z minus z0 less than rho, right? So we have so this is less than rho. Okay. So less than rho pi d square gamma. Okay. And by computation, this is equal to epsilon. Yeah. Okay. So with our specificity, we want the function value is very close, say within the epsilon. Okay, and then we try to find a disk. Okay, center with z0 and with sufficiently small radius to assure that the difference is less than epsilon, and we find that we can find such a rho just by saying this one, okay, by doing this assignment. Okay, and so we just but here we require that the rho is less than d minus 2, d divided by 2. So so we should say minimum. So to fix that, we should say rho is the minimum of d divided by 2 of epsilon pi d square gamma. Okay, we should ask rho should be the minimum of these two numbers. So of course, if epsilon is very small, then this number will be less than d over 2. But we just for in case that epsilon is taken to be a big number. So okay, so that Okay, so so I have to say, so this is less than or equal to epsilon pi g square gamma times gamma pi g square. So this is epsilon. Okay, so I have to say, because rho is less than equal to this number. Okay, so first of all, I have to put the inequality here. This is just for mathematical reason that we have to put that. Okay, so so actually by the epsilon delta definition of continuity, so we know index of z is continuous, right? At z0, right? And z0 is at any point, right? We say any point. So right. So we prove the function is continuous. The function is continuous. All right. So now we state a theorem. Or index. As I say, index can be interpreted as the one number of a point, okay, with respect to a closed tag. All right. So now, so we let gamma. Right. So actually, gamma is a closed tag in the compass plane. Omega is equal to the complement of the gamma star. Then the index function, okay, the index function in d gamma z the index function x and the integer value function. All right, omega. Initially, when we define the index function, we know it's complex valued. But now we will prove that the index function is integer value. Okay, integer value. Right, which is constant. Okay, so which is constant in each component. In each component, each connected component. Right. Well, as I if this is gamma star, now the complement of gamma star is three components, three connected components that we ask to be connected. So this is one component, right? One component. It's one component. Second, right? Another component is the second component. And then the third component is just our unbounded region here. Okay, so we have component like that one. So we have maybe we say so this is E1, E2, and E infinity example. So the omega is equal to E1, the joint unit E2, the joint unit E infinity. infinity indicate the unbounded connected component. Okay? So we have 3 connected components. Okay? So we say that its initial value and it's constant in each connected component. So in E1, the index value will be constant, and which is an integer. Okay, so and in E2, the index is constant value, and also integer value. And the integer value in here or here may be different or maybe the same. We just don't know. Okay, and outside in the unbounded component also every point here has constant index. It's constant index. But here we can address it. So in each connected component of omega, okay, and which is constant is 0, okay, in the unbounded. In the unbounded component. 0, particularly is E infinity. So every point in the E infinity has 0 index value. Okay? This is asserted by this theorem. Okay? So any questions about the statement? Alright. So first of all, you know, the complement of the cross paths, right? The omega, the open state, consists of several connected components. Okay, so for this example, we have 3 components, and we call it connected because we any point here to here can be connected by a line segment or well, just a chain of line segment. Okay. And so this is connected. All right, and we know particularly the index value of the point in the unbounded component should be 0. Okay, so it should be 0 here. Okay, so let's see how can we prove the theorem. Because it's very surprising, so I would like to give a proof. Okay, so the proof is here, right? Alpha and beta is the parameter interval of gamma. Okay, here. All right. So by definition, the index of z, okay, in omega with respect to the cross path gamma is the line integral of z in omega. Right? So from our definition of index, so it's just a line integral. Okay, so we use this term magnetization to express the line integral. So now we fix a point again in omega. So we fix the point. So z is a constant. We fix it. All right. So this should be a value, right? When we fix z, this should be a value, and fix that. All right. So note that, right? The index, right? Because we fix z, right? So this is a complex value in general, right? Right. So z is an integer. All right. If only that we raise write down the about 5 beta is equal to 1. Okay, where 5 t is defined in this way. Exponential function alpha t gamma x minus z and dx. Okay, so we use what? We use yeah. Okay. So so this one must be this is equal to 1 where the function is defined in this way, and the function is defined in here. Okay. So maybe it is too rush. Let me elaborate that. Okay, it is an integer, so that means that exponential 2 pi I index is equal to 1, right? So if the index if the index is integer, then we know 2 pi I times any integer number, the exponential value is equal to 1. Okay, because this is a complex exponential function, so we know that this is equal to 1. Okay, and so this implies that, but 2 pi I times index is this one, so that means that alpha beta gamma x as z dx is equal to 1. Okay, is that okay? All right. And now we define. So this implies that the 5 beta is equal to 1, where we define a function. Okay, we found a function to be exponential 3. Okay, so we define a function of t. Okay, in terms of the complex function, and so the function when t equal to beta should be equal to 1, because when t equal to beta, this is exactly equal to here, so it's equal to 1. So beta, so 5 beta equal to 1. Okay, so now we will focus on. So this is an only condition, right? Right. We want to show that the index is integer value. To show its integer value, we have to show that if we define a complex value function on this interval, the function value at t equal to beta is equal to must be equal to 1. Okay, so this is okay. And so now we focus on this function because the parameter t is real and it's in this finite first interval. All right. So now we differentiate. Okay. Phi t. Because exponential function is a nice function, right? We know that. So we have. So when we do the derivative, right? We find this is phi t, right? Because it is exponential function, so the same. And then we have to take the derivative of the exponent term. So the exponent term actually is gamma t, alright, and gamma t minus z. Okay, so this is our derivatives. Okay, except possibly a finite number finite set, all right, cos x where gamma t is not differentiable. Okay, because we know gamma is piecewise differentiable, so maybe at a certain point in this interval, this derivative does not exist. Okay, right? So when we take we use the chain rule, we have to show that because when we say this is true, if we have derivative, right? So this is true except possibly a finite state, all right? Where finite state, okay. So then we have phi prime t gamma t minus z minus phi t gamma prime t. Okay, so you can move the denominator to the left-hand side, all right, and take the difference between the right-hand side and left-hand side. So this is equal to 0. Okay. So that the derivative, okay, so the derivative of the function phi t divided by gamma t minus z. Okay, the derivative, because that the derivative exists in alpha beta, except the finite, except point in this finite set. Okay. So we know this exists, and then we know that the derivative, right? We know this is equal to square which is equal to 0. Okay. Right? Because the numerator, from here, the numerator is 0. Okay. So the new function, so this function is well defined, you know, because z is in the open set, is in the complement of gamma star. Okay, so the denominator is 0. So this is a well defined function. Okay. And its derivative exists in this set. And we find that it's 0. We find it's 0. Okay, so now the function of phi t gamma t minus z, okay, is continuous. Of course, because the phi t is continuous, of course, and the inverse of gamma t minus z is also continuous. So the product of two continuous functions is continuous. Okay, so this function is continuous. Okay. The whole interval, and we know with derivative, right? This is 0. Okay, in alpha beta and excluding x. And what kind of function, right, which is continuous and has derivative equal to 0? in the course interval except some point. What do we have? So the only thing is that it is constant. Okay, so it's constant in our i.e. So this function is constant. Okay. Okay. So that phi t gamma t minus c equal to k for all t in the interval. Right? So this is a constant. So this is a constant. In general, it's a complex value, right? A complex number, but it's constant. It's constant. And C. Okay? Now, since by definition, phi alpha, when t is alpha, the exponent is 0. Okay? So e to the 0 is 1. Alright? So phi alpha is 1, right? So we have okay, what is k? K is 1 gamma alpha minus z. Okay? We just put it, right? And then we know what is phi t. Because k is this number, right? Okay, so we know this is z. Okay. So now we know how to express phi t, right? So phi t actually is just this function. So you can see it's just the cos path, the gamma function minus a fixed because we fix z, right? Fix the complex number divided by some fixed complex number, non-zero complex number. Okay, so that remember when we put tau beta here, right? So we have gamma beta minus z, gamma alpha minus z equal to 1. Okay? And 1. Since gamma alpha equal to gamma beta, because gamma is curved. So what we prove? We prove that phi beta is 1. And this is what we want to prove, right? Okay? So this is what we want to prove. Because the index is an integer if and only if phi beta is equal to 1. And the phi t is defined here. So finally, so we prove this is 1. Alright? Alright, so we prove that the index is an integer. Okay? For all z. Okay. Because when we fix z in omega, we prove that index z is an integer. We already proved. So this is would be true for any z, right? So the index is an integer. Right? Now, any continuous image, all right, of a connected set is also right? So this is a property. So if you have, I just, I need that. Okay, so I say this is E1, E2, E infinity. So for this example, this is a component, right? It's connected. So a continuous function, because you can think about the index function is a continuous function E1. But because it's connected, okay? So its image, so the image should be connected. But the image, we know the image, the function value is integral value. Okay, so we see that. So we go to, we find that it has integral value 0, 1, and 2. Okay, this is an index function. Okay. So the index function goes here, etc. Alright? So the value can be only here, okay? Here, here. This is possible. Right? Now, and the E1, the image of E1 should be a connected subset of the complex brain, but it has to be what? Integral point. So the possible value of point in E1 cannot be different integers. Why? Because if you have two integers, say the range of E1 under the index function contain these 2 points. Okay? Now, but you can see that these 2 points, these 2 points cannot form a connected set. It's not connected. Alright? It's not connected. So this topological property, any continuous image, right? Because to prove this is continuous function, right? This is continuous function. So the continuous image of a connected set is also connected. So that means that, so this implies, strongly implies that in this function is an integer value continuous function on omega. So the index function is integer value and continuous function omega. Alright, so the conclusion is that so the index function must be constant. Okay, each connected component. Of omega. Okay, so we prove the first half of the theorem. So we prove the index function is integer value and is constant on each connected component. So the only thing we left is to prove that the index, right, corresponding to this unbounded component should be 0. Okay, this is the last thing we have to do. Now, also, when Z is sufficiently has sufficiently large magnitude. Okay? So Z is very far away from the origin, right? Very far away from the origin. The integrand. Okay? The integrand of the complex integral integral. Okay. In the definition of the index function is very small. Okay? So the integrand, remember what is the integrand? The integrand is 1 over it's minus Z, right? And when Z is very big, very big, no matter how cosine, because we know the cosine is here. This is cosine, and this is gamma t. Okay? It's local, right? This is always local. But when Z is very, very big, has big, very big magnitude. Now, so this one, so that the integrand will become very, very small. Okay, become very small. So that the index of Z, okay, is less than 1. Right? So the total value, the line integral should be very small, right? Very small. Right? And then the index should be 0. Because the index should be integer value, right? So the only integer has absolute value less than 1 is 0, only 0. Okay, so we have that in the unbounded component of okay, because that the index of Z in this unbounded component would be all the same, right? They are all the same because it's constant. So you just let Z going to the infinity boundary, okay? Going to infinity. So Z goes up, and so the integrand becomes very small, right? As small as possible. And so the line integral, actually the line integral is very small. So in particular, you say that the value of line integral is less than 1. And so you can see that the index is 0. Okay, so this is a proof of the 1E number, okay, or the index of the 1E number. Okay, and please see the remark. Okay, 14.1 in the supplement. Okay. In this supplement, I give a geometrical description of why it's called 1E number. Actually, just what I give the orientation display. So actually, the line integral is indicating that it is going to know the angles, how many terms that a point has been enclosed by the whole cross path. Okay, so it's called 1E number, and in particular, this remark gives you this kind of a description. Okay. Another remark. So I have. Okay, so we have to take a break.